In this video, we're studying Unit 3, Intermolecular Forces and Properties, Objective 3.1, Intermolecular Forces. Explain the relationship between the chemical structure of molecules and the relative strength of their intermolecular forces when the molecules are of the same chemical species or of two different chemical species. And our skill is model analysis. So what are intermolecular forces? In a previous unit, we focused on intramolecular forces, attractions within a molecule. This is really just a fancy name for covalent bonding. Inter means between, and these are forces of attraction that occur between different molecules. So here we have HCl, and this right here is an intermolecular force. That is a covalent bond. That is the sharing of electrons between hydrogen and chlorine. But in between our adjacent hydrochloric acid molecules, we have some attractions, and this is an intermolecular force. So between these two molecules, there's a force of attraction. And same with water. You never just really have an isolated water molecule. We have a whole cup of water or a sample of water. And so again, these bonds are covalent bonds. These are intramolecular forces, whereas these dotted lines indicate an attraction between adjacent water molecules or water molecules that are close to each other, and that is an intermolecular force. So we're now talking about the forces between different molecules. Because again, molecules don't just exist alone. We can't just isolate a molecule. We're normally talking about a molecule in a sample. So there's a lot of these molecules. So now we're discussing the forces in between those molecules. So our first key point is that London dispersion forces are a result of the Coulombic interactions between temporary fluctuating dipoles. London dispersion forces are often the strongest net intermolecular force between large molecules. Dispersion forces increase with increasing contact area between molecules and with increasing polarizability of the molecules. The polarizability of a molecule increases with an increasing number of electrons in the molecule and the size of the electron cloud. It is enhanced by the presence of pi bonds. So that's a lot of information. The key point is that London dispersion forces are a result of Coulombic interactions. So remember, we're talking about charge and radius when we talk about Coulombic interactions. These are the two factors that influence Coulombic interactions. And we're talking about the attraction between two different molecules with temporary fluctuating dipoles. So we've talked on the previous slide, we saw that HCl is a polar molecule. Hydrogen is less electronegative than chlorine. Therefore, there is a permanent slightly positive charge around the hydrogen and a permanent slightly negative charge around the chlorine because these electrons in this bond are not equally shared. They are closer to the chlorine because it is more electronegative. So the electrons here are slightly closer to the chlorine, giving chlorine a slightly negative charge and hydrogen a slightly positive charge. So that's a permanent dipole. Now we're going to talk about temporary dipoles. So these don't exist permanently. And so I'm going to show you what this means. So here are two helium atoms. The electrons are represented by the green lights, and then neutron and proton are in the nucleus. And the electrons are moving quickly around the nucleus. If we slow it down, notice at some point the electrons of one might be concentrated on one side, which induces a dipole because this side would have a slightly negative charge. And these electrons would repel the other electrons. So they would induce a dipole. So this temporary dipole on the first one induces a dipole on the second helium. And then because this side of the atom is slightly negative and this side of that atom is slightly positive, there is an attraction. But it only happens very quickly. It's very temporary because then these electrons begin to move. So that's London dispersion forces. And so again, It is a temporary dipole because the electrons are moving continually, and at some point they might be more concentrated on one side of an atom or on one side of the molecule, and therefore a dipole is formed, and then that can induce a dipole on a second atom or a second molecule. And these occur between all molecules. So every single molecule, polar, nonpolar, any molecule has London dispersion forces. And so this can occur if we just have a single atom, like neon. Neon can exist alone, or it can occur with a molecule like H2. So H2 is nonpolar. There's no permanent dipole, but these electrons in our H2 molecule are moving around quickly. And at some point, they might be more concentrated on the left side of the molecule, causing a instantaneous dipole to form. So the left side is slightly negative, the right side is slightly positive. And that can induce a dipole in the second one because the positive will be attracted to the electrons. The electrons will be attracted to that side. So this side of the hydrogen now has this side of H2 molecule now has slightly more electron density than the other side. And then there's this attraction, this London dispersion force in between the molecules. But it changes rapidly. It's not permanent. It is very temporary. There are a few ways to increase London dispersion forces. The first way is that larger amounts of electrons and a larger electron cloud could lead to stronger London dispersion forces. So here you see this box represents helium, this box represents xenon. So both helium and xenon are noble gases. They exist as just individual atoms. They won't really form bonds or diatomic molecules. And so helium is much smaller. Helium only has 2 electrons. So although there are London dispersion forces in between these helium, in between those helium atoms, they're only caused by the disparity of just 2 electrons. So when 2 electrons move to one side, that causes a temporary dipole, which induces another dipole, and so on. It can induce many, many dipoles because this positive side, the electrons of the central atom will be attracted to the positive side of the left atom and repelled by the negative side of the atom on the right. However, xenon has stronger intermolecular forces because instead of just having 2 electrons that can move, xenon has 54 electrons and a much larger electron cloud. So there can be many, 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 many more electrons concentrated on one side of a xenon atom than there can be for helium. And so therefore, this would be a much larger negative charge that can be created because of the much larger amount of electrons that xenon has. The second way is that larger surface area of a molecule leads to stronger London dispersion forces. So notice this gives us the element, the molar mass, and the boiling point. So boiling point is a good way to figure out what has a stronger intermolecular attraction, because if we have like a liquid here, when it boils, when it becomes a gas, the attractions between the liquid molecules have to break, so that way they can spread apart. So if it has a high boiling point, if it takes a lot of energy to break this attraction, then that means that there's a strong intermolecular attraction. There's stronger London dispersion forces, or there's stronger forces between molecules. It takes more energy to pull those molecules apart because there's stronger attraction. And so notice methane has a boiling point of negative 161.5, whereas butane has a boiling point of practically 0, of negative 0.5. So butane has a much higher boiling point, about 160 degrees higher than methane. And it's also got a much larger mass. So the larger the mass, the more electrons. So the more polarizable it is. So this butane has many more electrons than methane, and so there can be a temporary dipole that's much stronger because there can be many more electrons concentrated on one side of butane than there can be on methane. So the attraction between different butane atoms, the attraction between different butane molecules would be much stronger than the attraction between different methane molecules. Due to the higher polarizability because of the more electrons that butane has. And also, we can increase the surface area. So notice these have exactly the same molar mass, but dimethyl propane has a boiling point of 9.5 degrees Celsius, whereas pentane has a boiling point of 36.1 degrees Celsius, so a much higher boiling point, and they are isomers of each other. They have the exact same chemical formula. The only difference is that these atoms in pentane are more spread out along the molecule. It's a linear structure. It has a larger surface area, and so therefore there can be many more points of attraction for the London dispersion force. So here we have these two adjacent molecules will be attracting each other. Okay, but there's much more space that these two molecules can attract each other. And so therefore, there's stronger intermolecular forces, there's stronger London dispersion forces between molecules of pentane because it's got that larger surface area. So check for understanding. The London dispersion forces are weakest for which of the following gases under conditions of temperature and pressure? So if temperature and pressure is the same, which one has the weakest London dispersion force? So the answer is A, hydrogen has the weakest London dispersion force because it is the smallest atom or molecule that's shown here. H2 just has 2 electrons, whereas O2, each oxygen has 8 electrons. So it's got a total of 16 electrons in that molecule. Xenon has a total of 54 electrons in that molecule. Fluorine has a total of, each one has 9 electrons, so it has a total of 18 electrons, and nitrogen has a total of 14 electrons. So H2 has the weakest forces. Check for understanding 2. Consider the molecules represented above and the data in the table below. Nonane and trifluoropentane have almost identical molar masses. You can see that here. But nonane has a significantly higher boiling point. Which of the following statements best helps explain this observation? Okay, so when we're talking about boiling points, we're talking about intermolecular forces. So we're not talking about intramolecular forces, which is what these are talking about. These are talking about specific bonds within the molecule. But boiling point, we're talking about the attractions between different molecules. So if we had another nonane molecule below this, let's say this was our nonane molecule, we're talking about the force of attraction between these two molecules because it needs to break in order for nonane to boil. And so our answer would be C. The carbon chains are longer in nonane than they are in 2,3,4 trifluoropentane. So there's a larger surface area in nonane, and therefore there are more spaces where attractions can occur between molecules, and therefore nonane is more polarizable because the electrons can move over a larger space and the attractions can form in more spaces. So it has stronger dispersion forces and therefore has a higher boiling point.